Hello, this is a demonstration in how to use the various technologies to produce a lesson in microwave amplifier design, a course which is delivered by Princess Sumaya University for Technology. The example that we have here at our hand is a microwave example stating that a microwave lossless transmission line is terminated by a load ZL equals 10 plus J times ohm. We need to find gamma, which is the voltage reflection coefficient, VSWR, which is the voltage standing wave ratio, YL, which is the admittance of this load, and the input impedance Zn if the length of the line is 4 centimeters and the frequency of operation is 3 gigahertz. The first thing we need to know is the normalized impedance of the load, which we divide by 50 so that 10 over 50 gives us 0.2 and 20 over 50 gives us 0.4. So the normalized impedance becomes 0.2 plus J.4. This is the value that we will take into the Smith chart, plot it there, and get all the rest of the calculations from there. Another point we have to take into account is how much distance is the load is apart or is far from Zn. To do that, we transfer or we convert the physical length 4 centimeters into an electrical length. Now, knowing that the frequency of operation is 3 gigahertz, we now calculate lambda, which is the wavelength. Lambda in this case is 3C, 3 multiplied by 10 to the 8 over 3 gigahertz, 3 over or multiplied by 10 to the 9, which gives us 10 centimeters for the wavelength. Now, we need to move 4 centimeters, which is equivalent to 4 over 10, which gives us 0.4 lambda. So this is the distance we have to move from ZL to the input impedance Zn. Now we plot ZL in the Smith chart. Let's go now into Kitab, which is a software, Kitab Studio software designed by students at PSUT for the use in the classroom and with interactive boards. But here we just use it as it is. Now we open a Smith chart, an ordinary Smith chart. We import it from the desktop of the computer into the Kitab, and then you can see that we can zoom in and out to see exactly how we use the Smith chart and how it's a good idea for the students to follow. Now the ZL that we want to do to plot, which is 0.2, and these are the circles that represent constant resistance circles. Here is 0.3, here is 0.4. Now this is the circle that we need. And then the intersection with the interactive circle, which is 0.4. So this is exactly where our value needs to be plotted. Maybe it's a good idea to plot it there, and maybe you could now write ZL, normalized just to keep track of where we are exactly in there. Now we go back to the tools of the Kitab. We put the origin, which is there, that's the origin, and then we move the other point into our point, and then we can now draw a circle using different color. We can use different color. Here we go to change the color. And now we can move this as you see, and we can write now, we can draw a circle. We take the compass now down to the scale of the, we can zoom to the scale. We zoom to the scale. And we can zoom more if you want. And we place this. This is the reflection coefficient magnitude. Here it is in the scale down here. There are a number of scales, but we use this one. Now we place the scale at the main point here. and then that gives us a reflection coefficient. We zoom to the reflection coefficient, and it's about 0.5. So we write up there the magnitude of the reflection coefficient is gamma magnitude is 0.5. All right, we put it there. Now we need to find the magnitude at the angle actually of gamma. So we need to go to the whole thing. Okay, we go to the tools, we bring the ruler, and we put one point in the origin, and another point passes through. And now we draw a line which crosses it's not necessary, but I prefer it to be done this way. It crosses the whole of the Smith chart. Now we can remove the ruler, and now we can say that the magnitude, we zoom, and this is the magnitude of reflection coefficient, angle of reflection coefficient here, which is the second scale up. So the angle is about 136. So we can write there that the angle, the gamma angle equals 136 degrees. Okay, we can also determine the VSWR if we zoom into the intersection of the circle that represents ZL into the right, the intersection at the right side with the real axis. We can see that zoom, yes, we can see that the reflection coefficient is about the VSWR is about 5.8, 5.9, because it represents the intersection here, the intersection of this ZL circuit with the real axis, and we estimate the nearest resistant circle. Here we see that the nearest resistant circle is 5, here is 10, so that would be 6, 7, 8, and so this is about 5.8, 5.9. So we zoom out, and then we write down the text that the VSWR is equal to around 5.9, I would say. So we have determined two values so far. Now we go into the admittance. The admittance is the intersection between the constant magnitude circle, which represent the load ZL, with the line here at 180 degrees from ZL. So it's somewhere there. Now there we read the real part and the imaginary part. The real part, you can see it is the nearest resistance circle, and it's almost 1 here, because this is the resistance circle, which is equal to 1, and that is the reactive circle, which is 2. So really, YL is equal to, we said, when minus, because it's in the upper half of the Smith chart, plus 2, and that is the value of admittance that we have for this Now we need to know Zn. Now we know that the distance that we have to move from the load, which is there now, to the towards the generator, because there is no other way you can go except towards the generator because you are at the load. So we move at this scale, which is wavelengths towards generator. From where? From ZL. So where is this random value at this the last scale here? It's 0.062. So it's about 0.062, and we add to it, as we agreed, 0.4 lambdas. So we really need to go to 0.46 at the wavelength towards generator. We're here. We need to move to the point which is equivalent to 0.46. No. Here. 0.46. Let's find it. Let's zoom and find where it is. So now we need to locate the value 0.46 on the scale, the outer scale of wavelengths towards generator. So it's going to be somewhere, yes, here, there. So now we mark this. We mark it with any color. Now we draw a line. We place a ruler here, and then we draw a line. Let's choose a different color. Yeah, from the origin. Let's choose a different color. Whatever, and draw a line from that. Okay, all right. And the important thing here is remove the ruler, please, and then the intersection between the line and the circle that represent ZL. Remove it. Just. All right. And now we read the value of the real part and the imaginary part. We can see it's around point. The 0.18, and then the imaginary part is around 0.28. Is it 0.28? 0.02. 0.024. So we zoom out. You can see. I'd like here to use a pencil to show you the value of the real part is actually somewhere here, which is around 0.2 or 0.18, and the value of the imaginary part somewhere here, which you can see this is 0.1, this is 0.2, so this is 0.3, so it's about 0.34. So the value of zoom out, so we can write here text Z in equals 0.19. It's in the lower part of the Smith chart, plus 0.24. So that's the value of the normalized admittance. We have to impedance, sorry, we have to multiply by 50 to obtain the value of the, and that is the questions finished. Thank you very much.